Okay, so we've got this pile of resources all about collisions you sent us,
Yeah.
and we're going to dive into them. Looks like the main one is a 2D collision simulation with some billiard balls.
Right. Yeah, billiard balls are a really good way to visualize some of the physics that's going on with collisions like momentum and energy transfer.
Yeah, makes sense. And the simulation itself is from Open Educational Resources / open source physics at Singapore. It's even interactive, so you can actually like play with it and get those balls bouncing around.
Yeah, that's really cool. Hands-on stuff is always a good way to make physics a little more engaging.
For sure. I'm already feeling like I need to brush up on my physics a little bit.
Huh?
So this main simulation, it's called 2D Collision, and it was made back in 2017. The author's name is listed right on the page, and it looks like it's even open source, which is really cool.
Oh, definitely. Open source is great because it means anyone can use it, adapt it, even translate it if they need to.
Awesome. Now, you didn't stop there. You gave us a whole bunch of other resources on collisions too, like 10 of them. It's like you're making a whole collision course, haha.
It seems like you're approaching this from all angles. You've got some more interactive simulations, articles from places like physicsclassroom.com, and even one about the International Space Station.
Okay, the International Space Station one has me really intrigued. How do collisions even work in microgravity? Do things bounce differently?
That's a great question. The basic principles are the same, but the environment definitely changes things. Gravity plays a huge role in how objects act here on Earth, but in space, it's a whole different story.
So are you saying that in space, like, things could just keep moving forever after they hit each other?
Pretty much. There's no significant gravity to slow things down.
Hmm.
So objects will just keep moving at a constant velocity until another force acts on them. That brings us to the concept of momentum.
Okay, so break that down for me. What is momentum?
Basically, momentum is a measure of an object's mass and velocity. In a collision, the total momentum of everything involved has to stay the same, even if the momentum of each individual object changes.
So, like, even if the speed or direction of those billiard balls changes after they collide, the total momentum of all the balls stays constant.
Exactly. That's the law of conservation of momentum. And that International Space Station resource you mentioned probably goes into how this applies to space, where even a tiny collision with something like a little piece of space debris could have a big impact.
Yeah, I've heard those tiny pieces of junk can really mess up satellites. It's like a whole other level of impact, literally.
That's why understanding collisions is so important. It's not just some theoretical thing. It has real-world applications like protecting our stuff in space.
For sure. Now, I noticed in the simulations you included, some of them focus on something called the coefficient of restitution. What's that all about?
Ah, the coefficient of restitution. It's often represented by the letter E, and it basically tells you how bouncy a collision is. It's a ratio that compares the speed of objects separating after a collision to their speed when they were approaching each other.
So a perfectly bouncy collision where no energy is lost would have a coefficient of restitution of 1.
You got it. Think of a super bouncy rubber ball.
Mm.
But in reality, most collisions are inelastic, meaning some energy gets lost, through things like heat, sound, or even the objects getting deformed. A ball of clay hitting the floor, that doesn't bounce back very much at all.
Oh, yeah. That's a good example. So by messing with these simulations, you can actually see how different coefficients of restitution change the way things bounce.
Exactly. And that's what's so cool about them. You can manipulate the variables and see what happens. It gives you a deeper understanding of how these things work.
It's like a virtual physics lab. Now, I see you also included stuff other than just the simulations, like some articles and even a video analysis project. It's a pretty diverse bunch.
Yeah, well, collisions are pretty interdisciplinary. They're relevant to all kinds of things, like physics and engineering, but also sports and astronomy. It's all connected.
Speaking of connections, one of the resources even talked about how car safety features are designed using the ideas of momentum transfer during collisions.
Absolutely. Engineers use that knowledge to design things like crumple zones in cars. Those are the parts that absorb the energy from an impact to keep people safe. That's a perfect example of how physics helps make our cars safer.
Okay, so we've talked about the simulations, momentum, coefficients of restitution, and even car safety. Anything else in these resources that jumped out at you?
I'm still really interested in that International Space Station one. I think looking at how microgravity affects collisions could be really interesting.
Yeah, that one's definitely calling my name too. Let's check that out next.
All right, let's take a closer look at that International Space Station resource and see what's up with those microgravity collisions.
I'm ready to go orbital. So I get that gravity is pretty much non-existent up there, meaning things just float around. But how does that change how collisions actually work?
Well, think about it like this.
Hmm.
When you throw a ball here on Earth, gravity pulls it down, right? It makes that curved path.
Yeah.
But in microgravity, that ball would just keep going in a straight line until it hits something.
Okay, so no curveballs in space. Got it. What about the actual impact itself? Would a collision in space be stronger or weaker than one on Earth?
Hmm. Well, the force of the impact really depends on the mass of the objects and how fast they're going, whether there's gravity or not.
Hmm.
But the big difference is that here on Earth, we've got friction and air resistance that help slow things down. In space, that's basically not a factor.
So things in space are just bouncing around with almost nothing to stop them? That makes those little pieces of space junk even scarier, right?
Exactly. Even a tiny speck of paint, if it's moving fast enough, can do some serious damage to a satellite or the space station. It's like a high-stakes game of billiards up there.
Yikes. This resource mentions something called a hypervelocity impact. What is that exactly?
Oh, a hypervelocity impact is when something slams into something else at super high speeds. We're talking kilometers per second. And in space, those speeds aren't unusual, especially when you consider how fast things are already moving in orbit.
So it's not just the size of the debris, it's how fast it's going that makes it so dangerous.
Exactly. The faster something is moving, the more kinetic energy it has.
Yeah.
So even a small object can pack a massive punch if it's traveling at hypervelocity.
I'm starting to get why studying collisions in space is so important. It's not just theoretical physics anymore. It's about protecting our astronauts and the equipment we send up there.
For sure. Researchers are always working on ways to deal with the risk of space debris, things like shielding and tracking systems.
Wow, it's a whole new world of collision science up there, all because of the challenges of space exploration.
Definitely. Now, while we're on the topic of space, I want to bring this back to momentum, something we were discussing earlier. Remember, momentum is about an object's mass and velocity, and the total momentum has to stay the same.
Right, like those billiard balls. We said that even if their speeds and directions change after they collide, the overall momentum of all of them together doesn't change.
Exactly. Now, imagine two astronauts out on a spacewalk. They're both just floating there, at rest. If one pushes off the other, they'll both start moving in opposite directions.
Okay, I can picture that. But how does momentum fit into that?
Well, before the push, their total momentum was zero because they weren't moving. After the push, they both have momentum, but in opposite directions.
Yeah.
So the momentum of one astronaut cancels out the momentum of the other, meaning the total momentum is still zero.
So even in space, with no gravity, that rule of conservation of momentum still applies.
It does. It's a fundamental principle that governs how things interact, from tiny atoms to entire galaxies. It's a pretty big deal.
Wow, that puts things into perspective. Now, before we leave space behind, I'm curious about those other resources you sent, the ones that aren't about simulations. What else can they tell us about collisions?
Those resources give us a broader view of how we study and use the principles of collisions in different fields. Like you included an article about the physics of car crashes, for example.
Yeah, that one talked about how understanding momentum helps engineers design cars that are safer in a crash. They use things like crumple zones to absorb energy and protect the people inside.
Exactly. And there's also that resource about physics in sports, which looks at how collisions between players or with the equipment affect the game.
I'm picturing a baseball bat hitting a ball or a football player getting tackled. All those impacts involve momentum, energy, even the coefficient of restitution we discussed earlier.
Right. The ideas we've been talking about, they don't just apply to billiard balls or spacecraft. They apply to tons of things that happen every day, all around us.
It's like collisions are happening everywhere, all the time, whether we notice them or not.
Pretty much. Now, I think we should circle back to one of the key resources you sent us, that interactive 2D collision simulation.
Okay, yeah. Let's take another look at that and see what other cool things we can find. All right, so we're back to that 2D collision sim. I gotta say, playing around with it, it's pretty neat seeing these billiard balls bounce every which way.
It really is. And it's a great way to get a handle on some pretty complex ideas. So what kinds of things have you noticed while you've been experimenting with it?
Well, one thing I noticed is that you can change stuff like how heavy the balls are and how fast they're going at the start. And it's really interesting to see how that affects like what happens when they hit each other.
It is. It lets you isolate different variables and see how they change the momentum and energy involved in the collision. For instance, what happens if you make one of the balls a lot heavier than the others?
Let's see. Okay, I made one ball way heavier. Now when it hits one of the lighter ones, the lighter ball just goes flying off super fast.
That's momentum in action. Remember, the total momentum has to stay the same. So if a heavy object hits a light one, that light object have to pick up a lot more speed to balance things out.
That makes sense. So it's like a trade-off, right? Heavier object, less speed. Lighter object, more speed.
Exactly. Now, what about that coefficient of restitution we talked about?
Yeah.
That's something else you can tweak in the simulation.
Oh, yeah, right? That's the bounciness factor. A value of 1 means a perfectly bouncy collision with no energy lost. And I can actually see that happening here. When I set the coefficient to 1, the balls just keep bouncing forever.
Yep. But of course, as we said in the real world, most collisions aren't perfectly bouncy. They lose some energy along the way because of friction, heat, things like that. And you can see that in the sim too by setting the coefficient to something less than 1.
Let's try that. Okay, yeah. Now the balls are slowing down with each bounce, and they eventually come to a stop. Feels a lot more like real life.
And that's a good reminder that these simulations, they're really helpful, but they're still just simulations. They can give us a visual, help us understand things, but they can't perfectly capture all the little details of the real world.
Good point. It's always good to remember that models and simulations have their limits.
Definitely. Now, thinking about all the resources you sent our way, the simulations, the articles about space junk and car safety, what really stood out to you? Anything that surprised you or made you think differently about things?
Honestly, what really surprised me was just how many different things involve the basic principles of collisions. We talked about making safer cars, understanding what happens to debris in space, all sorts of things. It's pretty amazing how these fundamental physics ideas show up in so many different areas.
It really shows you how interconnected the physical world is, whether it's billiard balls, cars, or even stuff happening out in space. The same basic rules are at work. It's all connected.
And that's what I love about physics, finding those connections, those patterns that help us understand how the universe works.
Couldn't have said it better myself. Well, I think it's safe to say we've explored these collision resources pretty thoroughly. We dove into simulations, broke down momentum, even took a trip to the world of microgravity collisions.
It's been quite the deep dive. I feel like I have a whole new understanding of how collisions work and just how important they are.
Well, hopefully this exploration has given you some things to ponder. Maybe you'll even start noticing all the collisions and interactions happening around you every day, things you might not have paid much attention to before.
For sure, it's definitely been eye-opening. And to our listener who sent us all this great material, thank you so much for giving us the chance to really dig into this topic.
Absolutely. It's been our pleasure. Until next time, keep exploring and keep those minds colliding.